£50 million in energy network innovation, because the challenge of rapidly decarbonising our energy networks is enormous. But we can do this. With collaboration, we can make the leap. A giant leap together. We need the bravest, brightest, boldest change makers from across the world to work with Innovate UK, Ofgem and the Strategic Innovation Fund to create the energy networks of the future. The best ideas targeted at the most pressing challenges that reduce emissions and save consumers money. Join us now. Take a giant leap together with the Strategic Innovation Fund at ofgem.gov.uk. The strategic.
Hello everyone, and thank you very much for joining us for what promises to be an insightful set of show and tells covering the Strategic Innovation Fund's Discovery Heat Challenge projects. My name is Matt Hastings. I'm the Deputy Director for the fund over at Innovate UK, and I'd like to start just by sending an enormous thanks to all of the participating energy networks, especially the innovation teams and their third-party partners who have put in the hard graft during the last couple of months to get to this stage. Now, as with any new process, it can take you out of your comfort zone at times. There can be niggles and areas for improvement, but you've embraced this new discovery mechanism head on, and for this we are hugely grateful. The Strategic Innovation Fund has a very clear vision: to deliver net zero at lowest cost to consumers and turn the UK into the Silicon Valley of energy. Whilst it's hard to say given the current external environment, we do feel that by working together, we can make the UK the best place in the world to be an energy consumer, and the best place in the world to be an energy entrepreneur too. Supporting UK consumers and driving business growth to deliver net zero is why we are all here. Our mission has three major pillars: strategic alignment with other funders and other sectors, delivering fully in Agile, not just the challenges, but the discovery, alpha, beta mechanism, and the way that the SIF team operates on a day-by-day basis as a unit, and critically to focus on business as usual and commercialization of innovation. We're trying to discover the new products and services of the future that will benefit consumers, drive down costs and emissions. It's about consumers, the planet, and business. This is the core purpose of the Strategic Innovation Fund. And as per the animation, we're on this giant leap together towards decarbonisation. None of us have a monopoly on great ideas. Working together across the sector is how we're going to succeed. And GLT, as it's affectionately called, not to be confused with BGT, Britain's Got Talent, although somewhat similar in a lot of ways, has these four key phases. Challenge setting, and you will have seen we recently released our round 2 challenges for launch in September. Targeted ideation, where we point great ideas at great networks. Incubation, where networks can build their award-winning consortia. And acceleration, where the challenge is open and we will join the ENA, Ofgem, BEIS and the networks in hosting the first ever UK Energy Innovation Summit on the 28th and 29th of September in Glasgow. The round 1 discovery projects you're going to hear from are in acceleration. And if you talk to some of the teams who've been delivering, they'll recognise that it's been quite intense. But speed is essential here. We need to move quickly. We need to take risks and deliver the value consumers are looking for as fast as humanly possible. And let's pause a little bit to talk about the F word, failure. Some of these discovery projects will have failed. This is not a dirty word. This is the very nature of discovery. And these should not be judged negatively, quite the opposite. A positive failure to us equals a quick learning. It equals a faster route to find the best solution. Instead of just fail fast, we prefer learn fast. And that is what the SIF is all about. Finally, I just wanted to thank the Innovate UK team, David Richardson, Kate Jones, and Mani Ravishankar on the innovation team, and Christine Kunik, Tom Poole, and Amy Oswin on the PMO. I'd also like to just say thanks to Paul Whittemore on comms and our new colleague who's also joined us on commercialisation, Paul Padaruth. Also, a big thanks to our monitoring officers and expert panels. They have all worked incredibly hard to support the discovery phase, and without them and without our network colleagues and their third parties, there would be no fund, there would be no action. So thank you all for your hard work to get to this point. The best is yet to come. I'll now hand over to Kate.
Can I just check, are you guys seeing my screen at the minute?
Yep.
Great, thanks everyone. So like Matt said, my name's Kate Jones. I'm one of the innovation leads on the Strategic Innovation Fund. And we've got a treat for you this afternoon. We've got 5 of our heat projects talking about what they've learned from the discovery phase. So this was our first round of heat challenges that were open to the transmission electricity networks and the gas networks. And this challenge focused on developing those insights and findings to facilitate decision making in low carbon heating, not just for the networks, but the industry and government more widely. So the projects to date have finished their discovery round. That's focused on the feasibility side of things and what the size of the prize is should the project progress to the next phase. Again, just to kind of reiterate what Matt said, a big congratulations for the teams for getting to this stage, and hopefully you'll have some really good insights coming out of today. In terms of housekeeping, the format for today is those 5 projects. We've grouped them together, so we'll have a couple of back-to-back presentations with an opportunity to ask questions at the end of our grouping. We would like you to put any questions in the chat, and we'll get all the presenters back on the screen after the groups to answer some of those questions. Just in case there's any presenters on the call today, I'm going to control the slides, so you could do the next slide, please, and I'll follow along with that. So there is also a break halfway through, so you can get a chocolate biscuit, but today's session is recorded and will be made available to you. And just as a wee teaser at the end, Matt's mentioned about our challenges and our next round of challenges. We'll be sharing some more info on that at the end of today if you've not already heard about that. So for now, if I swap slides, let's have a look. Oh, I've kind of gone over these, so we'll flick through these. So for now, I'm going to hand over to, is it Jeremy or yourself, Kenny, that I'm handing over to first on flexible heat?
I'll kick it off, Kate.
Okay, thanks, Watson.
Okay, well, good afternoon, everyone. As Kate's sort of mentioned, well, I'm Watson Pete from SP Energy Networks, and I'll be joined by 2 of our project partners, Jeremy Harrison from Delta EE and Kenny Cameron from Connected Response, to tell you a bit about our flexible heat, what we found in our flexible heat discovery phase project. So if you change the slide, please, Kate. Yeah, so what's the problem that we're addressing? It's decarbonisation of heat. At the moment, the majority of heat in GB is supplied by gas. As we move to electrification, the heat demand is many times greater than the current demand for electricity. So electrification of heat will overload the electricity networks and require major investment in reinforcement. What we want to do is be able to make heat much more flexible, able to reduce the peak demand through that. So next slide, please, Kate. And the way that through flexible heat, the method we've been investigating is using smart control systems in conjunction with domestic thermal energy storage to unlock that flexibility from heat. And we've assembled this strong group of partners that you see here to work with us on the discovery phase project. Next slide, please, Kate. So in terms of the opportunities that we've been investigating, firstly, there's the technical solution as an alternative to network reinforcement, and that's smart control from the sort of DSO regional control system through service provider and aggregator platforms to the end user consumers with the heat pumps and potentially thermal energy storage in their homes. We've been looking at the commercial side of things, so how can customers be incentivized to use this solution? What are the benefits, particularly what are the benefits for the electricity networks and as well as other parts of the energy system? And we recognise that customers are key to this. Customer engagement is crucial, so we have a specific work package on customers. So I will now hand over to Jeremy Harrison from Delta. Thanks.
Thanks, Watson. Okay, next slide, please. So, as Watson said, the key focus of this project has been about the need to provide flexibility which will avoid or defer network reinforcement. So that is the key priority overall, and that's the one that we note here in terms of the user needs. But there are other benefits and other needs which are being met simultaneously. So although we focus on avoiding the network reinforcement, in doing so, we also capture some other benefits for the wider energy system, for example, by minimizing curtailment of renewable generation. That has benefits for the ESO and, of course, to wider society. The alignment of heat demand and electricity generation has benefits to the end consumer in terms of possibly lower cost of energy during the periods they need the electricity, and of course, again, to the network operators as well. And the other benefits there accruing to other participants, other stakeholders in the energy system, right down to the bottom where you have the carbon intensity of the electric heat by shifting the load from high carbon intensity generation periods to lower periods. That has a wider societal benefit. The next slide, please. So this project is focusing on, as I say, the shifting of load from peak to off-peak periods to defer network reinforcement. And this is predicated on the assumption that the electrification and decarbonisation of heat through electrification is by replacing natural gas-fired boilers in central heating systems with heat pumps using renewable electricity. So just as a baseline here, a diagram for those of you who aren't familiar with them, typically in a normal central heating system, you have a gas boiler with a primary circuit feeding radiators with hot water, and also within that circuit you have the domestic hot water cylinder providing sanitary hot water, and sometimes a buffer tank to provide some sort of capacity in the system to manage the way the heat pump works. So this diagram here shows the baseline operation with a central heating programmer deciding when the heat is required and the temperature it's required at, but with no communication to the outside world. So there are two components here. One is looking at the way in which we manage that controller from what Watson referred to earlier, the regional control platform. But then there are also the physical assets, the storage of energy in terms of the domestic hot water cylinder within the buffer tank, also within the fabric of the building itself. So the technologies we looked at, starting off in a kind of hierarchical fashion with the simplest interventions. So using smart controllers to capture the value of the thermal inertia in the building itself, because we believe this is clearly the lowest cost intervention, and then progressing through the hot water cylinders using thermal buffers and then primary thermal stores and other technologies, including more advanced concepts like phase change materials, and also indirectly using electric storage as a kind of a proxy for the heat. And we also looked at a number of complementary technologies and innovative technologies, and as I say, in a hierarchy from the lowest to the highest cost. The next slide, please. And then, of course, there's the overall the control platform. I'm not going to talk very much about this because I think that Kenny from Connected Response will talk a bit more in a second. But just to say that the layers that we're looking at are the intervention with the home central heating programmer using a behind-the-meter technology, and then aligning that with the demands of the wider network. And of course, in between that, there is some kind of mechanism which combines the commercial flexibility, adding sort of an economic dimension to the smart control. Next slide, please. And the simple conclusion that we found, not a great surprise, is that it is possible to use the thermal storage technologies to provide some level of avoided peak load. What we wanted to demonstrate, though, was whether that was going to be a more cost-effective solution than network reinforcement. And in simple terms, what this summary of one of the scenarios is, shows from sort of left to right the simplest intervention, the one in sort of relatively dark blue there with the 588 above it. That was for a simple controller which simply switches off the heat pump during periods of peak demand to reduce the demand on the system, and uses the thermal inertia of the building to maintain a certain degree of comfort during that period. But of course, it's a fairly crude solution, and some people may find that that doesn't give the level of thermal comfort that's necessary. The next solution there, the one with the NPV of 1231, that is a smart controller applied to the same concept, which is to use the thermal inertia of the building, but rather than just switching it off, we elevate the temperature of the building prior to a peak demand period so that the temperature can then just drift down gradually. The third one there, the 1081 NPV, that is using active thermal storage in the form of a primary thermal store, which is essentially a large hot water tank, very similar to the hot water cylinders you find in a house anyway. But that enables you to maintain comfort in a much more controlled way than you will just by using smart control. Beyond that, you see that suddenly the investment in more complex and sophisticated storage technologies significantly erodes the value of the concept, and the values are captured from, as I mentioned earlier, the deferred investment or avoided investment in network, and that represents about half the value that's captured. Other values include things like flexibility payments, the ability to switch to lower cost wholesale price periods, and clearly you want to try and capture as many of those as possible. So what this is simply showing is it is possible to avoid and certainly defer network investment, which will facilitate the incremental heat pump rollout without having to go for a big step change in having to make a big network upgrade just to accommodate a few more heat pumps, which is one of the key factors which is going to facilitate the rollout of electric heat pumps to decarbonise heat. And I think with that, if I can then hand that over to Kenny to talk about the controls and the customers.
Thanks, Jeremy. I'm Kenny Cameron, the Managing Director and co-founder of Connected Response. Our key focus is in the 1.5 million homes in Great Britain that have electric storage heating and hot water by fitting smart controls to improve comfort and cost, but also working with the likes of SP Energy Networks on projects in Glasgow, where we're doing a 10,000 flat rollout at a rate of 50 a week with Scotland's biggest landlord. The starting point on this project as a team was to pose the question, what can we learn from the last major electric heating rollout, which was the rollout of storage heating in the 1980s, there or thereabouts. And the lessons from history on that would be that with hindsight, it was never really about customers. It was all about disposing of surplus nighttime nuclear generation. And so we were determined in this to say, if this is an even bigger rollout that has to be done, how do we take customers with us? And for any of you that have lived with storage heating, you'll know what I'm talking about. No one in this day and age would ever launch a system and say you can only have our commodity of electricity for a few hours a day, starting at 11:30. So the key message is customers must embrace new technology or it won't happen. They must understand it and they must know what's in it for them. The transition needs to be done with customers, not to customers. We've assembled a great team in this that Watson talked about earlier on, and a good diverse mix of SP Energy Networks, academics, manufacturers, energy services providers, consultants, and we all come to it with great projects we've been involved in. And when we sat down at a workshop at the beginning of discovery phase, the challenge was to say to all of us, forget all the glossy things, all the wonderful good news stories that we all preach about our projects, but what went wrong? What did we get wrong in these projects from a customer perspective, and what lessons can be learned from that? Did we visit them too many times? Did they not understand the operating instructions or the original communications materials? or did we fail to follow up post-installation? So we started to draw out all the things that, that people would do differently. The other thing then was we involved Wheatley and Warmworks in that, Wheatley being Scotland's largest landlords, the owner of Glasgow Housing Association, and Warmworks being the managing agent for Scottish Government's fuel poverty and energy efficiency works. And that was very valuable in that it gave us the chance to learn over a wider base. And Wheatley offered to support E.ON as one of the partners within the consortium to help to arrange the trial. Okay, so the next thing then that we did was I want to talk about, if you turn the slide please to the next one, was just to give you a brief overview of some of what's been talked about already and the 4 key elements within the alpha phase. There's 4 work packages. For the technical work package this time around, we were planning to bring in a new partner, and that's Smarter Grid Solutions, often known as SGS in Glasgow. And they're going to be looking at a high level, a regional control platform, and what would need to be put in place to control all this dispersed and disparate loads. Within that package, there'll also be a close zoom in on the behind the meter control solutions to understand what controls are out there at the moment, what is the communication systems these controls are operating on, how much does that vary from building to building, how much does it vary across geographical areas, what's the interoperability, and what is the speed at which that service can be provided. So all very important. The case study will be led by E.ON. It will be owner-occupiers as well as social housing tenants. The commercial and regulatory is to look at how the benefits will be split. Who should benefit from, say, flexibility revenue? Is it landlords? Is it their tenants? How will we disperse those benefits? And in regulatory, to look at some of the problems that might stop us from doing any of the things we want to do. So there may be a need for regulatory sandboxes to give freedom to the project if it goes to alpha, then beta, to do what needs to be done. And finally, on the customers, we're planning to bring in there as a subcontractor the Energy Systems Catapult to be involved in supporting the customer interviews, in particular because the Catapult, as some of you might know, have recently begun an initiative with funding from Scottish Government to partner with the Power Network Demonstration Centre at Cumbernauld, specifically to set up a living lab in Scotland. So we think that's going to be a real value both for alpha and if we're successful as we get through to beta phase. So that's a very quick run through the aspects within the alpha bid. And I think we're ready for questions and hopefully answers as well then.
Yeah, thanks, Kenny. We're actually going to go to one more project before we come to you guys for questions. So thank you for that. So if anyone's got any questions for Watson, Jeremy or Kenny, please put them in the chat and we'll come back to those in just a minute. We're actually sticking with Scottish Power and I think we'll be back to yourself, Watson.
Yes, thanks, Kate. I'll do the introductions again. So this time is to talk about our second heat project, heat balance. And again, I'll be joined by 2 of our partners during this, Bobby Joe Milligan from Ramboll and Professor Daniel Friedrich from University of Edinburgh. So if you could go to the next slide, please, Kate. So the problem, again, is the electrification of heat. And as this graph shows, the current demand for heat, the current peak demand for heat is many times that of the current electricity demand. There's a huge variation in heat demand between seasons as well as within each day. The demand for heat doesn't necessarily correspond with the output from non-dispatchable renewable generation sources. So in terms of the future energy system, there's going to be a huge requirement for long-term, large-scale energy storage of all kinds in order to balance that system. Next slide, please. We also have a problem with transmission constraints on wind generation. As you can see from this constraint map, the particular issue is from north to south, so generation connected north of the border be transmitted to the south. And we know that renewable generation needs to quadruple in order to meet our net zero targets. So it's a situation that's expected to get worse, and the constraint payments associated with that Scotland-England boundary are expected to peak at £1 billion per year. So next slide, please. So the opportunity that we see is quite, in sort of simple terms, is to use the curtailed wind energy, particularly in Scotland, to charge large-scale thermal energy storage, which can then be used flexibly to supply heat to heat networks. As I mentioned, all forms of energy storage are going to be important. Large-scale thermal energy storage is one of the lowest cost forms of energy storage. So, next slide, please. So to the discovery phase of the project again, we've assembled this strong team of partners to work on it with us. Two main areas of focus: a technical work package looking at the sort of practicable options for large-scale thermal storage in GB, and a commercial work package that looks into the benefits for the wider energy system, particularly the electricity networks. So I'll now pass you over to Bobby Joe Milligan from Ramble.
Yeah, so the next stage then through the technical development was to look into what the user needs are for the network and for this sort of opportunity. And we've identified that the two key benefactors are going to be obviously the electrical network and distributors, as well as existing and new district heating networks. And we need to provide a way of identifying a pathway to deployment of such a large thermal energy store, as well as, oh, I've just lost your presentation there. There we go.
I think that was just me having a blip with the cable.
You're all right. I understand the business case for developing a large thermal energy store and how that sits within an existing district heating or a new district heating network potential, and as well then what key geology requirements and there are for capacities of district heating networks. The other thing then, of course, is the parallels with the electricity network is how does the distribution work, how can the solution be facilitated, and what is the full potential of the flexibility that's there for using curtailed wind or constrained wind. Next slide, please. So large thermal energy storage is an existing concept and it's utilised quite heavily across Denmark, the Netherlands, and all the other Nordic regions. And so it's an active way of using renewable power and using it usefully whenever it's out of phase with the demand of electrical networks. So as we've been saying, that your electricity may be constrained at a time when your heating isn't required, which obviously your summer months. And so large thermal energy stores can be used in the meantime to store the energy and use it whenever it's not going to impact your high capacity electric network. 4 key item types identified. You've got your aquifers, your pits, your boreholes, and your mines. There are many examples, ranging from the 8 to 10,000 meters cubed all the way up to the hundreds, and the most recent in Graz is 800,000 meter cubed capacity. Next slide. So the findings through the technical work package were that there is this difference between the electrical constraint and the demand for heating. And so the electricity network can use thermal energy storage as a way of frequency response and balancing. As we've said, that heating is going to move away from gas and there's going to be this higher use of electricity for heating in the network. And so even though at the moment there's constrained use and we're using capacity that's otherwise unused, we're still adopting the highest options. It's not a matter of just throwing immersion heaters everywhere. It's looking at COPs of more than 4 on heat pumps and that sort of technology. When looking into the geology of the UK, we've looked at the level of aquifer potential and we've identified about 4 million gigawatt hours, which is an unfathomable number whenever it comes to the demand for heat and its utilisation. As well as in the mid-countries, there's the identification of mines that have huge potential. You know, there's projects underway at the moment, not using it as storage, but using it as a direct use for heat in the likes of Newcastle. And there's a significant expansion of district heat networks at the moment through the Green Heat Network funding and the HNDU project. So we could see in the future a much greater potential need for thermal energy storage whenever we're looking at heat networks. And I'll pass off to Daniel.
Good afternoon, everyone. So I will talk a bit about the commercial work package. One of the things which Watson said is that we have this massive mismatch between heating demand in winter, which is massively larger than in the summer. So we need to supply this from non-dispatchable renewable power plants. And if we quadruple our renewable generation and we get rid of all the gas generation in the electricity system, we also get rid of quite a large chunk of flexibility in the system. So we need to add this flexibility back into the system so the network operators can run their system most efficiently. And this is where storage comes in, from short-term storage to longer-term storage to balance between seasons or months. And this diagram on the left shows a bit the benefits storage can have on the system. So there's things like managing the networks, avoiding or deferring reinforcement, and this can be reinforcement of the grid, as well as peaking plants. We can improve power quality and also the system control. And all these systems have added benefits. Some of them are benefits on the operating costs or of the capital cost of the system, but there's also environmental benefits because we will use our renewable generation more efficiently. Watson said that some of the wind farms in Scotland, they are curtailed for 30% of their output. So this is basically wasted renewable capacity, which we have already paid for to build these things, and now we're paying extra to curtail them. So we should use them more efficiently, and this would then reduce the need for backup generation in winter. So these are sort of the general benefits seasonal storage can have, or storage in general. So in this system, we looked at a feasibility study for an existing district heating network, and we replaced their heat supply with electric heating, heat pump, as well as resistive heaters, and with a seasonal thermal storage system. And this system would preferentially use curtailed renewable generation. So this is generation for which we currently are paying that it's not generated. And we showed, and I will give some numbers, that we can reduce requirements for network reinforcements. We reduce the carbon emissions for the system. Going from an electric heating system which uses grid electricity to curtailed electricity has very low carbon savings, but if everyone goes to electric heating, we probably need peaking plants in winter, which will most likely, for the foreseeable future, be using natural gas, which has much, much higher carbon intensity than our electricity grid, particularly here in Scotland. So we reduce the emissions by neglect or by removing the need for more peaking plants in winter as well. And we can shift the energy purchase to low electricity periods, and this can help us balance and support the electricity system. Next slide, please, Kate. The graph on the left shows a bit of an output for our case study. So the blue, the highest line is the weekly electricity demand which we need for a heat pump run system. If we replace this with, or we add curtailed electricity, so what's shown now is all the energy which we need, which is not the curtailed energy. And we basically reduce our winter electricity demand by about a third. As you can see, the two lower curves, one is for a heat pump case, one for a resistive heater case, are reasonably flat throughout the year. Obviously, are slightly higher still in winter, but we managed to flatten the demand quite significantly by using curtailed energy on top of grid electricity. And this, as I said, reduced the winter demand by about a third. This has follow-on implications for the deferment of the grid infrastructure. So we showed a positive internal rate of return for these projects. but we also showed that we can reduce the need to strengthen the connections between Scotland and England with this. So for Kilgalleoch wind farm, which is one of the most heavily curtailed wind farms, about 30% of its output is curtailed, we can run about 100 of these district heating networks. And we estimated that we have cumulative benefits up to 2040 of about £440 million by getting rid of extending the transmission grid. So seasonal thermal storage can have a massive impact to provide low carbon as well as financially beneficial energy for district heating networks. Next slide, please. So looking ahead to the alpha phase, the discovery phase showed that it can work. All the bits of the technology exist, but it hasn't been implemented in the UK, and there have only been very few cases where it has been implemented as this multi-stakeholder system. Usually seasonal thermal storage systems are run by a single company who also owns the district heating network. Here now we are looking at a multi-stakeholder system where we have the district heating network operator, the storage operator, as well as the grid. So we need to think about more commercial frameworks as well as regulatory frameworks. So the regulatory frameworks and barriers for the heat storage, how that links to the network to ensure everyone can sell their electricity, has enough heat for the winter. So this is the main problem, that the technology exists, but we need to provide blueprints to roll out this technology at scale in the UK. So we will look at a guide and evaluation matrix to look at archetype district heating networks linked to curtailed energy as well as subsurface storage in the UK. We will have a closer look at the socio-environmental factors, because people might not be happy if we heat the ground below their feet or we reuse old mine working. So we need to look at the social implications of this as well as the environmental implications. And finally, we are going to develop a demonstration project which can act as a living lab to de-risk future schemes, to test this integration, and to pave the way for a massive rollout of this technology, which could save significant amount of money as well as emissions in the future. Thank you very much.
Thanks, Daniel. I welcome everybody that has just been presenting. So Watson, Jeremy and Kenny and Bobby back on the screen, and we'll take some of the questions. Stop sharing so I can see everybody. Okay, let's have a look at some of the questions we've got in here. Okay, so coming to the flexible heat project first, what sort of duration of storage in approximate hours were you looking at to get the main benefit of avoiding peak loading of the network?
Okay, so generally speaking, the peak electrical demand on the system occurs between 5 and 8 in the evening, usually the very coldest day of the year in the middle of winter. So the modelling was focused on avoiding any electrical demand during that period. It was a fairly simple model where, as I say, we prioritised avoiding electrical demand during that period. But the modelling was based on a generic network. It wasn't looking at a specific location. And in the alpha phase, we will be focusing more on an actual geographic location and a real network, and looking at the actual load profile on that network. But generally, it's between 5 and 8. Rather than just looking at the coldest winter day, though, what we did was to take half-hourly periods right through the year, because we wanted not just to look at can we avoid power consumption during that period, but what is the impact on, as I mentioned before, the wholesale time of use, cost of electricity, the carbon intensity of the grid at various periods. So we did that throughout the whole year to understand the value that shifting from that period can achieve.
Thank you. We've got a fair few questions, but we're ahead of time, so I'll just stick with flexible heat for a little bit longer. Will the thermal store replace the hot water tank, or will the householder need to find space for a second tank?
Well, what I would say is that most of us with gas heating have now got combi boilers and don't have a hot water tank. So finding space for some kind of thermal storage will be an issue in a lot of houses. One thing about, for example, phase change material thermal stores is that they're more compact than hot water tanks. They've got higher energy density, so that can be a potential reason for using those in preference to hot water tanks.
Thanks. Do you have any data on the proportion of homes that still have hot water tanks, and do those without have the space to accommodate? So it's somewhat similar, I think we've probably covered. Do you have any data on the homes that do have anything? Do you have a hot water tank even?
I think there's, just to pick up on what Watson was just saying there, that the majority of homes have switched to, or more than half, so about 60% of homes with gas heating systems have moved to combi boilers. So replacing those boilers with heat pumps is going to be an issue, whatever we do. That's one of the big challenges in applying heat pumps and electrification. So you start off with the hands, you've got to have some form of thermal storage anyway, and typically there will be a need for a hot water storage tank. Where we have modelled what we call the primary thermal store, that is replacing that hot water tank and the buffer tank as well, actually. But as Watson says, the reason we looked at the more sophisticated storage technologies like phase change materials was to find a solution which you could have a physically smaller store. But that is going to remain one of the challenges of rolling out heat pumps in all homes.
So I know you touched on some of the work that you're doing with the phase change material, but is the project looking at anything about the developments in that space?
So during the technology review, we did look at the both the existing commercially available and some of the more leading edge, say, phase change materials, but also some of the technologies with a lower TRL level. But what we were really looking at was, are there practical technologies available? We didn't want to focus so much on the technologies themselves, but what they can deliver. So when we did the modelling, we, for example, said, in order to achieve a avoidance of that peak period, how much storage do we need? So let's say it's 9 kilowatt hours, for example, on a typical evening. And then we said, okay, so that amount of storage can shift the load from that period. We then looked at, okay, now what technologies can give us that amount of storage? So indirectly, yes, we looked at a very wide range of technologies, but the NPV demonstrated that the simpler ones are actually the most cost effective to do.
Thanks, Jeremy.
Kate, can I just go back to your earlier point? You asked the numbers. The numbers that are easier to quote as real numbers are the houses already with the electric storage heating that already have hot water tanks, and that would be in Scotland, say 12% of homes. And one thing that's clear from all the smart control work that's going on there is there's huge opportunity to move that charging around. There's many people that are having their hot water charged 8, 10, 12 hours before they use it, and they're still happy with the system. So there's a big untapped potential there.
Thanks, Kenny. This might be still one for you, Kenny. So regional control platform sounds like networks directly controlling heating devices. Is that how you see the world needing to work in the future versus, say, this being run through a commercial arrangement in flexible markets? Maybe one for you and Watson there.
It's probably Watson to kick it off, because it's more a question of perhaps future policy, and that's maybe not for me to.
Yeah, I'll jump in there. So I think it's a combination of techniques. We certainly see that that flexibility markets can take us, can provide a certain amount of flexibility, and particularly a fairly fairly local level. However, what we're looking at in terms of low voltage networks becoming overloaded, we may be needing to have very granular control over the loading on networks, and in that instance we believe that sort of direct control solution has a place as part of the mix.
Thanks, Watson. I think just kind of jumping back to another question that we had on the phase change materials. There's a specific question here, Jeremy. Did you explore thermochemical storage, which is more energy dense than phase change materials?
Yes, so that's when I was referring to some of these sort of TRL levels, which are not at commercial stage. So things like zeolites and so on. And they can actually have quite long duration. But we were focusing on a mass rollout of heat pumps, and therefore we were focused on mostly on commercially available products. So not the more more complex things which need more space, for example, which can give you longer term storage, but looking at products which are readily commercially available and which are reasonably well understood. But it is true that these thermochemical technologies can give you a much higher energy density simply because they are not dependent on the temperature difference between the store and the demand, which is actually one of the practical issues as well. It's all very well saying you've got, say, 9 kilowatt hours of energy storage. You've got to get that heat out in a usable temperature. So whether you're using that for domestic hot water, where you need it maybe at sort of 65 degrees or so, rather than space heating, where you might have to lower temperature around 50, you have limits on the usability of that heat. And the great thing about phase change materials is that they deliver their heat at a fixed temperature. They do it at the temperature which it changes phase. So that's one of the benefits, not just the fact it's a higher energy density, but that it's much easier to extract the heat in a usable temperature.
Thanks, Jeremy. So just a question to kind of try and bring the two projects in now. We've just had from Linda Forbes on the chat here. Have either projects considered impact of climate change to potentially flatten heat demand curve, i.e. less in the winter, cooler in the summer?
Maybe I can, if no one wants. We haven't considered it yet, but it's on the cards for the alpha phase project. When I spoke about the archetypes of linking district heating networks together with curtailed wind energy, so we're looking at projections based on the future energy scenarios of national grid to look at curtailment for the future, as well as IPCC scenarios for changes in temperature.
Thanks, Daniel. Okay, so we'll come on to some of the heat balance questions now, but feel free if there's crossovers on the flexible heat also to jump in. So was the thermal inertia just that already exists, or did you explore the impact of increasing the thermal inertia of homes?
I think that actually applies to the flexible heat one. The answer is simply no, we didn't. So when I talked about the hierarchy of technologies, thermal inertia of the house was the lowest cost. Basically, that's there already. And the only additional cost is the cost of the smart controller that you need to control the heating system. We didn't look at adding thermal inertia simply because it probably would have been cheaper to use active thermal storage, which is what we're looking at. So no, we haven't looked at adding thermal inertia to buildings.
Thanks for picking that one up, Jeremy, as well. Okay, well, we'll try and get a heat balance one this time. We'll see. I'll find the hardest one. Are you talking about constraint payments that result from insufficient network capacity or curtailment because there isn't enough demand anywhere?
I think primarily it's due to insufficient network capacity. However, the solution would help in both instances, but you certainly think that the primary cause is the network capacity across the boundary. Daniel, would you agree with
that? Yeah, I think certainly at the moment that's the case. My opinion is that it's probably once we quadruple our renewable generation capacity, we will have both of these problems, as Watson just highlighted, and the technology can work for both. So it doesn't matter why the energy is curtailed.
Thanks, guys. Would investors in large-scale thermal energy storage need longer-term revenue mechanisms relative to what we have today to cover risk?
Yes, I think, well, that's seems likely. Yes, well, I think we need to investigate in more detail, but it would certainly seem likely that for the kind of scale of infrastructure investment that we're looking at, sort of contracts that only lasted for one 5-year price control period might not give that level of confidence that the developer would need.
There's a question about, can you say more about the megawatt hour? What megawatt hour comes per cubic meter of thermal storage?
Yeah, I've seen that one come through. If you assume like a 20,000 kilowatt hour demand to the average home, that value quickly adds up to 20 billion. So you're going to beat them all. That's basically it. You'll heat every home.
Yeah, I think there was two questions. There was a question about how the storage potential equates to the number of homes, but I think there was also one about how much energy stored in a cubic meter, which I guess is going to depend on the particular temperature of the particular storage system. That's
it. So it depends if you're working on an ambient loop system or if you're working on a high temperature system. But in this case, you're probably talking at the 90 degrees C. So on your delta T of 20, you're talking your megawatt.
Thanks, guys. Okay, I'm just looking through some more of these questions. What is the counterfactual assumed in the commercial analysis? Distributed thermal energy storage, power flex, demand side response, gas turbines, or no flex? Not sure.
I'm not sure if that is for the flex heat or for heat balance.
I think it's come under the heat balance timing, but if we've not got any takers.
No, I'm happy to do it if no one else wants. So we consider that the heat network is there because there are existing heat networks and they need to decarbonize. Most of them are running on natural gas combined heat and power plants, and they need to change away from that to something which is close to net zero at least. So we compared our solution to one which had electric heating with a heat pump for the system. So we added the seasonal storage to that and additional electric heaters and compared it to this system because this is one of the options for them to decarbonize.
Thanks for that. Okay, another question we've got is, did you calculate the impact of the economics of the heat demand reductions that will result from home energy efficiency improvements that are needed to meet government targets? So they put, for example, the EPC rating C, lower peak demand equals less need for shifting storage, lower opportunity to curtail generation.
Well, certainly efficiency improvements of homes is really important, and it has to be a starting point before heat pumps are installed. So we start from the position that homes are brought up to a suitable insulation standard and heat pumps are installed, and then look at what flexibility we can achieve on top of that.
Thanks, Watson. So last heat balance specific question, hopefully. Do you have estimates of what the costs are creating district heating networks to use the heat from thermal stores?
I can maybe explain that a bit like in flexible heat, in the way that we've assumed, that there is going to be a rollout of heat pumps. Similarly with heat networks, for example, in Scotland, the Scottish Government have a target of, I think it's 6 terawatt hours output from heat pumps by 2030. So we start from an assumption that these heat networks are going to be rolled out, and therefore what benefits can we achieve by adding thermal storage with them.
Thanks for that, Watson. Okay, so just something that probably needs to come up for both projects, but what have each of the projects done to look at customers in fuel poverty and how they can be better served by these options rather than the status quo?
If I can maybe pick that up first, that within the Flex Heat project, that's why we've involved Wheatley as Scotland's biggest landlords, owning and managing about just under 100,000 properties across the whole of central Scotland, from Dumfries up to Glasgow and beyond. And also we involved Warmworks in the early discussions as well, because they are the the ones that are disbursing Scottish Government's energy efficiency and fuel poverty payments. So I think that we felt we talked in discovery phase about this being work package number 3, being customers and stakeholders. So the customers we've talked to directly, and for the stakeholders, we've taken Wheatley and Warmworks as a proxy for representing the customers. So I think that's crucially important. I think that it's dangerous to assume in any of the discussions we're having that landlords are going to install the heating systems that policymakers want if they've already had bad experiences. So I think involving landlords in particular is very important.
Thanks, Kenny. And on the heat balance side?
Well, I think that being able to use the curtailed wind energy, if there's a way to sort of benefit from the savings in curtailment payments to reduce the cost of energy, then that's going to help any customers who are on the heat network, including those in fuel poverty. There may be more specific regional benefits in terms of the areas, perhaps East Ayrshire being an example where there's a huge amount of constrained wind and also significant fuel poverty. If there are mechanisms to to use that curtailed wind energy to benefit the people in that area.
Thanks, Watson. We're ahead of schedule, but that's all the questions that we've got in for these 2 projects. So thanks very much to all the presenters. We have a little break scheduled in already. So we'll take a wee 10-minute break just because we've got the presenters lined up for at times. So on my watch, it's 1:57, so we'll be back by 2:07, and we'll pick up on the remaining 3 projects. Thanks again for the presenters.
Thank you.
Thank you.
Thanks.
Thanks, Kate. For those who've just joined, we're just having a 10-minute break. We'll be back at 10 past.
Hi guys, welcome back. We have 3 more projects to go through on our heat challenge. So these projects are focused around insights into the hydrogen decisions. So the way that we're running the session for anybody that's just joined is we'll have 3 presentations now, and at the end we'll do a Q&A for all 3 of the sessions. So what I will do is the next one that we have up is the charge project. Gemma, am I handing over to you first?
It's going to be Steve's going to give us the introduction.
Yes.
Great.
And then myself and hopefully Mab will talk through some of the project stages.
Great. Well, I'll hand over to Steve if he's here.
Yes, I'm here. Can you hear me, Kate?
Yes, I can hear you fine. Just tell me when you want me to move on the slides.
Right, okay, then I should begin. So thanks for that, Kate. So good afternoon, my name's Steve Johnston, the Senior Innovation Specialist in National Grid Gas Transmission, and I'm joined today by the project partner representatives from Project Environmental Solutions Limited and Mark McDonald to give you an overview on the outputs from the emissions capture or charged SIF discovery project. So next slide, please. So as the UK progresses towards net zero by 2050, National Grid Gas Transmission must seek innovative ways to minimise its methane and future hydrogen emissions. So where technological solutions are required that can be easily integrated as new or retrofitted to existing rotating machinery equipment, this is to reduce or eliminate compressor shaft seal vent or planned compressor vent releases. The SIF discovery phase of feasibility into conceptual design work has delivered all the planned SIF discovery key work packages originally defined, such as confirming the need case, selecting a feed consult with a request for information completed, selecting the technology and sites for possible pilot installations, and launching the original equipment manufacturer's request for proposal. This has provided a clear understanding of the challenges, opportunities and costs associated with the pilot and future rollout as business as usual solution, along with laying the foundations for a pilot plant capable of capturing methane emissions for re-injection on a live gas transmission compressor station as we transition from a methane to a hydrogen-based system. Now I'd like to hand over to Gemma Priddick and Mab Rashid from our project partners, who are going to take you through some more of the detail behind the work packages delivered during this phase of the project. Thank you.
Thanks, Steve. So Steve's outlined, we were lucky to start the SIF discovery phase with a fair amount of momentum. We had sort of proved our need case and we demonstrated feasibility of our technologies, and we'd narrowed that technology selection down to methane capture and recompression, specifically of emissions from process vents and seal gas vents. We'd launched an RFP, and with the sort of sprint nature of SIF, we'd asked for a fairly rapid response and turnaround from our OEMs, the suppliers of these technologies, and we gave them a sort of phased, we allowed them a phased return basically just because of the speed and nature of our request. This slide outlines the 7 work packages which we sought to achieve. They were split into 2 sort of main focus areas, really. The tasks at the bottom half, tasks 1 to 4, work packages 1 to 4, were focused on the evaluation of those potential supplier responses. So we wanted to look both technically and commercially and also environmentally at their proposals. As I say, we'd already sort of demonstrated in an earlier stage of the project that the technologies in question were feasible. We believed them to be feasible. And really, we were now looking at, I guess, assessing the readiness and how developed their conceptual designs were. The tasks 5 to 7 were sort of internal facing project tasks, really aimed at moving the project towards that pilot study and rollout as necessary. So those are sort of pre-works. The bulk of the tasks, I guess the focus of the technical and commercial evaluation were to look at the readiness of the designs and to consider whether those designs had taken into consideration all of the integration and safety issues that would be of concern to National Grid. So there was a significant amount of sort of compliance or high level compliance review. We engaged with a series of subject matter experts from within National Grid and the feed contractor to look at the functional specification that we might eventually issue out to any selected supplier. I'll just check Mab's on the call because I can't see his name.
Yes, I am, Gemma.
Oh, you are. Perfect. Okay. If you want to pass on to the next slide, I'll hand over to Mab to go through some of the sort of outcomes and achievements of those 7 work packages.
Yeah. Hello, everyone. Mab Rashid from Mott MacDonald. I'm acting as the design coordinator from this company's side, and my background is a process engineering background. I'll take you through a quick rundown of the kinds of activities we engaged in service of these work packages, focused a little bit more on the procedure rather than the eventual results. Just in case people in the audience are curious, we started this process thinking that there would be one eventual winner, and we do indeed have our favorite vendor and second favorite and so on. However, it's too early in the process to go into those details, we feel, because there's still a great deal of design work to be done, which the vendors will themselves bid for. So to give you a quick rundown, work packages 1 and 2, as the wording goes there, were technical, safety, and engineering evaluations. So this was really looking into the nuts and bolts of the proposal put forward by the vendor, as early stage as those were. It was to look at whether the vendors had thought about the typical operational problems and the typical issues that come up in a realistic implementation. So side by side, there were work packages 3 and 4. Those were focused on looking at what National Grid was asking for and whether that needed any modification, whether there were any ways in which the functional specification asked for by the client could be modified to bring it closer to a successful implementation. There can always be things which are asked for in the standards, but in reality, they're perhaps onerous or too rigorous in practice. So as the next set of bullet points in the middle of the slide shows you, sorry. Thank you, Kate. As the next set of bullet points in the middle of the slide shows you, the focus was on the differentiators between the designs of the 3 vendors and identifying any possible showstoppers, any big roadblocks along the way, which could be seen from up ahead, seen from the current stage of the project, and therefore some mitigation plan could be worked out for them. As I say, there's fine-tuning of the functional spec to make it realistic, and that informed our view of the success criteria, as it shows on the right-hand side of the slide, the success criteria that we would be applying to the designs produced by the vendors in order to eventually come to a decision later on in 2022, hopefully, on who would be the front runner, the favorite among the vendors. At the moment, I have to say there is a possibility that there could be more than one design that could be carried forward, because all of them have good points and bad points, as you'd well imagine. Gemma, shall I let you go into work packages 5, 6, and 7 for a little bit?
Yeah, sure. As I mentioned, I guess these are sort of pilot pre-work stages and necessary project governance steps in order to move the project closer to that pilot that we hope for. We developed a stakeholder engagement schedule, considering all the sort of voices that needed to be heard, I guess, in developing things like the functional specification and assessing those integration challenges and differentiators. We worked on a carbon footprint estimate and also renewed the BAT assessment based on the updated and more detailed information that we'd received as part of the RFP. That was really a benchmark and exercise to make sure that the environmental case for the works for the whole of the charge project stacked up, and we were happy to say that all the packages offered by all the vendors, the carbon footprint for implementing those solutions was dwarfed by the potential savings that they offered. So there'll be no concerns there about either financial or environmental payback. And then we mapped out sort of future and further pre-works and sort of phased those formal environmental assessments that would be necessary to take the project forward. And all of that basically, as I say, is a sort of a step along the road to an eventual pilot. Next slide, please. The outcome
Gemma.
of, hi.
Oh, should I take over some of this?
Yes, sure.
Yeah. Okay. So to continue our story, the recommendations that we can inform all of you of at the end of this SIF discovery process are outlined in this slide. We are going to continue the request for proposal process, the RFP process. It doesn't come to a hard stop at the end of SIF discovery. There are still plenty of questions to be answered, plenty of clarifications to come from the vendors. So we expect this to go on for quite a while. And alongside that, we'll have our discipline specialists from Mott MacDonald and discipline specialists from National Grid asking the relevant technical questions, kind of probing further into the designs and looking for strong points and weak points. The eventual aim in the next few months is to get to fixed delivery costs for the pilot studies that the vendors will do. Now, they themselves are tasked with producing a cost estimate for the design phase of the work that they would each go through. And when we're looking at those cost estimates, we're looking for a realistic proposal given how mature their designs are. So for instance, the designs which are less mature would need a lot more work. We expect them to cost for it. So that's the approach we're taking. As I mentioned, a preferred supplier will be taken forward, hopefully later this year. As things stand, the integration and control requirements of the vendors' packages is one of the big themes that we feel we'll pursue in the rest of this year. As you can imagine, the package that comes on board these compressor stations, the control system has to be able to talk to the existing control systems. So that's one of the chief things that will determine how easy or difficult the implementation is. PESL and ourselves at Mott MacDonald are keen on the next point, which is the pilot site selection and unit selection. As mentioned, it could very well be that more than one design turns out to be viable for these compressor stations. And then there will be an exercise to do to determine which designs suit which sites best of all. And so we expect that itself to be a workshop or a study on its own. So the next few points are about investment planning, regulatory implications, and safety reviews. Maybe for this one, would it be okay, Gemma, to pass to yourself?
Yep. So as Mab said, a key next stage is future investment planning and sight from that pilot to an eventual sort of implementation plan and a business as usual rollout if that's where the project takes us to. In order to prepare for that and also the detailed design phase, we are going to reaffirm our emissions reduction estimates and those potential benefit and outcome of charge. And that in itself will feed back into that site and unit selection. Because of the heterogeneous nature of the gas transmission network, there isn't really a single solution from a single vendor that could be applied across the network. Hence, as Mab said, the potential for there to be multiple pilots and multiple vendors selected for future rollouts. So we'll continue with those sort of pre-works and preparatory works, assessing the regulatory impacts of implementing these solutions, undertaking the formal safety reviews at a high level initially, and as we get further down the line of vendor selection and understanding more about the conceptual and detailed design, those safety reviews can delve deeper into the sort of concerns or constraints that we might see. Next slide, please. So this is our intention for the next phase. Although we would say that SIF discovery has been, on the whole, successful, and we have taken the project forward against all of the sort of work packages as outlined in the left-hand column of this page, there has been sort of, I guess, good news in that the project might be taken forward via an alternative means of funding. That might allow us in the next 6 to 9 months to continue to work on the aspects that Mab has just described, taking us towards detailed design, rechecking and reassessing those emissions reduction estimates, and considering in more detail the site and unit selection. All of that we believe would take us to detailed design starting early 2023. And if you flip on to the next slide, we would be in a sort of pilot build and commission phase early 2024. And beyond that, depending on the appetite for rollout, we could commence potentially multiple pilots alongside that first one on a sort of staggered basis, testing those different suppliers on those different scenarios and operating systems on the network, and then on to rollout if that's where the project takes us. Next slide. That's the end of our deck. So yeah, happy to take any questions in the session. I understand we're going to move on to another project first.
Yeah, thank you for that. Just a reminder for anyone that's just joined, if you put any of your questions in the chat, we'll pick that up for Steve, Mab and Gemma in a couple of sessions time. So we'll do the session. Thank you. For now, I'm going to hand over to Robert Best first, I think.
Yeah, that's correct. Yep.
Yeah, great, Robert. Hopefully, I think there's a wee delay on the slides.
That's fine.
There we go.
Fantastic. So good afternoon, everyone. My name is Robert Best. I work at National Grid Gas Transmission, and I was the project lead for this successful hydrogen barrier coatings for gas network assets SIF discovery project. So next slide, please. Next, yeah, thanks. So this project falls within the Innovation Challenge 4 heat, and the big idea here is to repurpose the national transmission system for green hydrogen instead of natural gas, which will provide a zero carbon heating for domestic and industrial users. So the NTS would provide, so the national transmission system will provide resilience and storage capability rather than relying on transient and localized hydrogen production. However, to operate at optimal efficiency, mitigation measures need to be put in place in order to manage the risk of hydrogen embrittlement of certain transmission system assets, such as the pipe itself. So this project addresses this via 3 main work streams. The first one is to apply a barrier coating to the internal surface of the asset, which will prevent significant hydrogen uptake. And that work stream was led by Ultima Forma, and Andy's on the call and he will talk us through those bits in a second. The next work stream was led by Warwick Manufacturing Group, and that was to identify new hydrogen-ready pipeline materials. So where we need to install new pipeline in order to enable the hydrogen future, or where we need to replace end-of-life pipeline. We're looking at options there, and Tom Hayes will talk through that, focused on composite and polymeric options there. And the third work stream was led by gas transmission and metering, and that was to determine the commercial viability of the various solutions to ensure the best value to the customer. Okay, so next slide. So we'll talk through each of the work streams in turn, and we'll start with the hydrogen barrier coatings. So the first step here was to communicate our user needs of a barrier coating to Ultima Forma. We did this via a series of meetings with subject matter experts from National Grid, in which we prioritised gas-facing assets and captured pertinent information to feed into the coating material and deposition selection process. So the kind of things that we kind of communicated over to Ultima Forma were the material grade, the surface condition, whether it had a coating or not on the internal surface. So that helped to identify the kind of materials compatibility requirements there for that. Other things such as the geometry and the access constraints, whether the component could be removed from the system or not, whether it had to stay in situ. All of those things would feed into Ultima Forma's selection of a suitable deposition process and also the materials that related to that. So the table shown there has the high priority assets identified there. So the 4 ones that we put as high priority are filter casings, the pipework itself, both above and below ground pipework, the girth welds that join those pipes together, and valves. So these were all very high, very common assets on our network, and so these were given a high priority. So I'll just pass over to Andy, who will talk us through the work stream in more detail. So next slide, please.
Thanks, Rob. In the discovery phase, we investigated a wide range of potential hydrogen barrier coating materials that you can see in this table here. And the most useful parameter for comparing materials is their permeability characteristic for hydrogen. So this data that we have on the slide for room temperature shows that the most effective hydrogen permeation materials actually come from things that are not very practical to apply at scale. So things like ceramics and even more exotic materials like single crystal silicon. They're brilliant, but they're not very useful for this kind of application. Of the practical materials, the metals provide significantly lower permeation values at room temperature than polymers, about 10 billion times lower. And of these, a subset of candidate materials was kind of identified out of that set that we could apply with well-developed technologies and at an appropriate scale. And these tend to be densely packed metals without their own hydrogen embrittlement characteristics that are kind of readily available. Next slide, please. So with this subset of metals in mind, we explored the potential deposition techniques that you could use that we could actually apply to National Grid gas network assets. We considered a wide range of aspects, including the coating thickness that we need to achieve, the volume of material that you need to be able to do that, any waste products, the quality of the coating, preparation and post-processing steps, and any significant process conditions that would be really difficult to achieve, like a high vacuum, for instance, that would be complete showstoppers to apply into the network. So these processes were considered in terms of their most critical use cases that Rob was talking about just now, that National Grid had identified, and whether it's possible to apply them, for instance, in the pipeline while it's still live with gas. Of these techniques, the 3 that are outlined here in red was considered as potential for further development for different types of assets, and this includes things like electroplating, cold metal powder spraying, and potentially hot dipping. Could we have the next slide, please? So part of that consideration was to think about the preparation methods that will be needed to convert the existing network and the existing condition into something that we could apply a coating to. We made a visit to the National Grid Ambergate site, and that was very informative in trying to understand the real condition of the pipeline components when they're in service. National Grid provided us with some samples, and we ran some trials on some of the preparation techniques, things like scratch brushing, grit blasting, chemical pickling, and so on. And these studies showed that there's a range of preparation processes that could be applicable for different barrier coating methods and allow some flexibility in the approach that we could use for different asset types. Next slide, please. So the combination of coating technology and candidate materials demonstrates that there are feasible solutions here that could provide a range of possible different solutions for different situations within the National Grid gas transmission network. We also considered the indicative costs for the material systems that we might apply based on coating a unit area of 1 square metre. And these calculations include the material and processing costs, but they don't yet include the cost of implementing that inside the gas transmission network. That's something that we'll have to develop further in the Alpha project. But at least it can be seen that there's a range of price points here with several relatively low cost technologies. And these will be investigated for implementation further in the Alpha project phase. So next slide, please. So in summary, for hydrogen barrier coating materials, there are materials and application methods that have been identified that are feasible for providing an effective hydrogen barrier coating to national grid assets. And there are different solutions available for different types of asset situation and type. Going forwards, it's going to be necessary to turn this feasibility into practical engineering solutions, and this includes a complete coating system, surface perforation, the application method, the material system, verification of that coating method, and assessment of the durability. So that will allow us to build up and get a system that could be applied in situ into the national grid gas transmission network. So Rob will present our plans for how we intend to do that in the Alpha stage later. But for now, I'll hand over to Tom Pice at the Warwick Manufacturing Group to introduce the new pipeline materials work package. Thanks, Tom.
Actually, just before that, I'll talk through the user needs. So thanks, Andy. So where is the barrier coating? So yeah, that slide, thank you. Whereas the barrier coatings looked at addressing repurposing of the existing pipeline, this next work stream focused on new materials for new pipeline installations. So the pie chart shown there just summarises an assessment of the transmission system to identify the most at-risk sections which might require replacement in the future. The user needs were communicated via a workshop with WMG and National Grid subject matter experts again, and the existing steel pipeline standards were kind of used as a benchmark. What we currently have is what we currently would like going forward, obviously without any hydrogen embrittlement risks, with a potential increasing in pressure and gas velocities to account for the lower energy density of hydrogen compared to natural gas. So if we move on to the next slide, and then I'll give Tom the floor.
Thank you, Robert. So yeah, at WMG we looked mainly at identifying the state of the art in plastic and composite pipelines. What sort of solutions are there out there already, and also we looked a little bit at what sort of solutions could come in the not too distant future. In that area, we identified basically two technologies. One is a glass fiber reinforced epoxy pipe, and we also identified the reinforced thermoplastic pipe systems. So glass fiber reinforced epoxy pipes, they're already used in the oil and gas industry quite regularly. They can be produced at large diameters, which is sort of necessary for transmission pipe systems, and they can also are able to withstand high pressure ratings. And they're produced typically at lengths of about 10 to 12 meters, which is relatively similar to the steel pipe that is already in use. The thermoplastic pipes, on the other hand, they can be produced almost at infinite length, but practical reasons they're sort of limited to maybe 1,000 meters because they are spooled. But the problem there, in a sense, with regard to using them as transmission pipes, is that because of the spooling, the diameter is limited to around maybe 6 to 10 inch. So relatively small pipes there. So in terms of identifying user requirements, as Robert already mentioned, basically steel pipes is the state of the art, and they work at 50 bar to maybe 90 bar and diameters of 500 millimeter plus up to maybe like a meter in diameter, which as I mentioned makes things very difficult for reinforced thermoplastic pipes as they are available at the moment. We also looked into the effect of hydrogen on composite materials and found that polymers, they're mostly unaffected by hydrogen. They don't show hydrogen embrittlement, at least a very wide range of polymers. But like as Andy already said, they do not necessarily have always the best permeability performance. In terms of how these pipes should be manufactured, in most cases this is done by helical filament winding. I'll show you an example of that after this. Joining can be done by adhesive bonding, which is quite state of the art, but still also needs may have some issues when it comes down to using hydrogen. But the technology does have can have a lot of benefits when it comes down to conditioning monitoring. In composites, the use of integrated in situ health monitoring systems is quite well established. So, for example, you can introduce an optical fiber technology into a composite. Next slide, please. So, in terms of reinforced thermoset pipes, as I said, glass reinforced epoxy pipes is probably the method that is being used currently most in the oil and gas industry, and can also be adopted quite easily for hydrogen service. So this is done by helical winding, which you see in the picture here. Basically, you wind strands of fiber which are impregnated in epoxy resin around the mandrel up to the thickness that is required to withstand, let's say, the pressure. These pipes, they have, at least within sort of the polymer pipeline system, they have quite good hydrogen permeability resistance. They can be produced, as I mentioned, up to large diameter. You know, they are pipes for, let's say, wastewater that are made up to diameters of 2 meters. They are unaffected by hydrogen embrittlement. They don't suffer from corrosion, and also have quite a low environmental impact. You know, if you do an LCA analysis of a polymer pipe system versus steel, they have quite a low environmental impact. Joining technologies available by adhesive bonding, well, current pricing of pipes with, let's say, a 50 millimeter pipe would be around maybe 350 pounds per meter. Next slide. So as an alternative, as I mentioned, the market, and there's quite a lot of movement in this area, is the use of reinforced thermoplastic pipes. So I think this is a very interesting technology because it's basically these pipes can be made in a continuous process. So the process involves basically an extrusion, which is a continuous, relatively cheap process. And in that case, it's a co-extrusion process, which together with overwrapping, helical wrapping of a reinforced tape and a barrier layer, which can be, like as in the picture on the top right, basically an aluminium foil or a thin layer of aluminium, but it can also be a polymer with much better barrier properties. So, for example, you could extrude a pipe which by co-extrusion, that means extruding 2 polymers at the same time, where there is a polymeric layer based on ethylene vinyl alcohol, which has very high, very good permeability properties or very low permeability, can be included directly in the process. But as I said, the processes or the technology that is out there is mostly limited to smaller diameters, which maybe rules out this technology for transmission pipes. Next slide, please. So in terms of summary, in terms of replacing steel pipes for composite pipes, probably glass reinforced epoxy pipe are currently the most suitable. They are the technology is basically available. There are some issues that need some attention. So, for example, if we go to really high pressure, so that means higher than 50 bar, close to 90 bar, the current pipes that are on the market are not already all there. And also in terms of very large diameters for hydrogen at these very high pressures. I think at the moment most piping systems are there at 600 millimeters. So if you want to like 1 meter, that would need some development. Of course, because these pipes are made in sections of about 10 to 12 meters length, the weakness of the whole piping system will probably be in the joining technology, because that's how good as the system would probably be. And there are still quite a bit of unknown factors in terms of the permeability at the joint, but especially in, let's say, how this is done in field, because this is done by adhesive bonding. Joining technology in steel pipes is very established, welding, and the welders that work in this industry are probably some of the most skilled and qualified welders that are available. Whereas in the composites industry, people that would be doing this sort of joining technology, there's no training, or there's no standards, etc. available. So there is a lot of catch up to be done to get, let's say, the standard and the quality assurance for an adhesive bonded joint in a piping system compared to, let's say welding of steel pipes. There's still a lot of development in terms of standard training that needs to happen. So I think that's where I leave. I'll hand over back to Robert.
Yeah, next slide, please.
Yeah, Robert, there's just 1 minute left, okay?
Yeah, so just very quickly, so we're moving into the alpha application, and we're concentrating on barrier coatings going forwards. The composite pipeline materials workstream will be pursued via other alternate funding routes, but for alpha we're going to concentrate, narrow the scope slightly in terms of just looking at barrier coatings. So WMG will be leaving the consortium and Rosen will be joining it. They're an expert in inline peaking technologies, and the aims of this project are to validate the coatings that Andy's talked about in terms of the performance, define a process feasibility for the in-situ deposition, so that will be led by Rosen, and then refine that business case and develop an implementation plan. So next slide. And then just to summarize, so we completed a successful discovery project looking at barrier coatings, new line pipe materials. The project was delivered on budget or slightly below budget and on time. 2 technical reports will be uploaded to the Smarter Networks portal. And as I just mentioned, the alpha application called Hints Protection will focus on barrier coatings with gas transmission and metering, Ultima Forma and Rosen. So thank you very much.
Thanks, Robert, and sorry to rush you at the end there, just to make sure we can fit everybody in. So just if there's any questions for this project, just remember to put them in the chat. We've got 1 project left, and then we'll be doing a Q&A session. So Mike, am I handing straight over to you?
Tim Elson, who's on the call, should be leading this one, supported by Jane.
Great. Okay, sorry about that, Tim.
Okay, thanks, Kate. I'll go until things get difficult, and I'll get Jane to help me. Our project is called Velocity Design with Hydrogen, and this is all about the repurposing of gas networks for hydrogen service rather than methane, or with blends of the two. So we've had a bit of a team on this, which is Dave Baxter, who's into fitness for service, me, I'm a integrity specialist, Jane, who does the network analysis, and Mike, the account manager. And Dave Gower was also on this, who can't be here today, and he's also a network analysis consultant. So if I have the next slide, please. The issue we're trying to address is really to do with the challenge to do with heat. I think, as people are saying, one of the issues is delivering enough energy to consumers for heating their premises. Now, for decarbonisation, for the gas industry, a elegant solution would be to deliver hydrogen rather than natural gas, because burning hydrogen only produces water and no CO2. However, the energy density of hydrogen is considerably lower, so we would actually have to put flow rates up by around 3 times for entirely hydrogen network to deliver the same energy to each house effectively. So this increase in flow rate actually means the gas in the pipe will move quite a lot quicker, so velocity goes up. So we need to understand how high we can go on the velocity, and is there a limit? And that's for two purposes really. If we're building new pipes, we need to know what the limit is, but equally, if we're using the old pipes, we need to know what they can deal with. And that directly impacts on basically the need for investment. Do we need to modify things? Do we need bigger pipes? This sort of stuff. Now, at the moment, we've got standards in the gas industry, and the common ones are produced by the Institute of Gas Engineers and Managers, Ofgem. And the common numbers basically don't go over 20 meters per second. If you think you might have debris inside your pipe, particles of different sorts, and normally speaking, people think that's to do with, it's effectively to do with erosion by the particles hitting things, or noise or vibration, or also an issue if you get fast enough. If you're pretty convinced your pipe hasn't got anything in it at all, you can go up to 40 meters a second. So that's quite useful. However, when we do some of the numbers, we can go actually above that on hydrogen. So we need to try and extend a bit. The other thing we don't know with hydrogen really is because it has quite different properties to natural gas, because natural gas effectively, everyone says it's methane, but it's got loads of other stuff in it. What we don't know is, will we actually pick up the things that are in the pipe and move them about? Or is there some other factor that we don't know about yet? So the part of the project is, what is the constraint? Is it erosion? Is it vibration? Is it noise? Or is it something that currently the standards don't address at all? Okay, next slide, please. All right, so this is effectively what we did. So the Discovery Phase project covers 4 aspects. We did a literature search to see with hydrogen and anything else, to be honest, what are these constraints? Is it moving the debris about, erosion of the pipe, erosion of customer equipment? Do the standards help at all? So we've got these TD1, which is high pressure stuff, and TD4, which is lower pressure stuff, and TD13, which is effectively the stations and installations which are dotted about the gas networks to do useful things like valves and pressure regulation and the like. Equally, those stations are things like compressors and the like on. So do we have a different problem with hydrogen on things like noise? So we wouldn't really want the very loud noises to appear, or the thing to shake itself to pieces. Will it make a lot of vibration? The other thing that is interesting is, does hydrogen itself change the way erosion works? Is there something extra apart from just hitting things very hard with particles. So the second aspect on the right there is, because we did this project with SGN jointly, is what debris is doing the networks. So SGN did some investigating, and we've been trying to correlate this across all the different pressure tiers in the different networks. Let's say, what have they found? What's the operational experience of finding bits and pieces in filters? When they do inspection vehicle runs, what comes out? When they do mains replacement, so they're replacing a lot of iron pipe, what's coming out of the iron pipe? And which network's basically got a lot of dust and other debris inside them, and is that related to pressure? Then there's the green bit, which is really to work out what work you need to work out the impact if we start changing the limits on design requirements or design outcomes. Because it could go either way. We might put the velocity up, or equally might put it down, which would be slightly unfortunate. And then you have to look at a cost-benefit analysis on, well, what's the benefit of, say, putting a lot of higher diameter pipe in, for example, versus just delivering less energy and thinking of something else, like electrification or partial electrification. And then the like grey box is determining what testing we need to prove it one way or the other, effectively, and what future testing can we do to basically validate any modelling or conclusions we come to, because we need to be very robust about this sort of thing. Next slide, please. So what do we find? So we found a lot of quite interesting things. The literature search indicated two aspects which may well become important. It appears possible that erosion in hydrogen is different to that in natural gas, in that you may well be able to get enhanced erosion rates due to synergism between hydrogen embrittlement and particulate erosion. And there's a relatively few papers that indicate there may well be something in that. The other thing that it showed is that moving the debris, particle transportation, would actually be significantly different in hydrogen to natural gas. Possibly wouldn't be able to shift as much. On the experience of debris, the SGN's experience is really we find that there's debris across all the pressure tiers. We find it all over the place. Some of the debris is different, but we find it. In the medium and low pressure systems, it actually has quite an impact, in that you can end up having to clean out networks. It fills up filters, gets into valves, this sort of thing. And in our report, we talk about the types of debris, some of which are more surprising than others, effectively. So when we looked at what work's needed to investigate the impact on design outcomes, so effectively what we concluded, so you do need to actually do some work to look at the impact of the changing the limits on the design of the networks, and that really comes to a quite complex modelling job, really, to look at how future demand interacts with potential replacement of mains and services in the low pressure tiers, and how you optimise the costs for consumers. it is quite a complex piece of modelling. Particularly, we're not quite entirely sure what the limit would actually be. And then determining the testing requirements. What we found really is that it's quite complex requirements for the testing for erosion, noise, and vibration. Because we think there's this potentially this synergistic erosion mechanism. You need to build something where you can test that or prove it for a start on laboratory scale testing. And if it's real, then build something big enough to do a realistic test to see if it's possible in something that looks very much like a gas network, and what happens to noise and vibration in that. Because we've done modelling and we think it does change. But the problem is the models we use are all calibrated for natural gas, and nobody's ever tried them in hydrogen, and it could be different. So for alpha, I think we're maybe on the next slide, but what we need to do is to design and effectively cost building this full-scale test facility that will allow us to get some realistic risk assessments effectively. So in alpha phase, what we propose to do is to go to all the networks and say, well, what, because we have SGN, but do the others see network debris? Is it different debris? And what sort of debris is it? Part of that is getting industry engagement. So we get everyone to buy in and say, yeah, we got to go to the Technical Standards Forum, which is how the gas industry makes new standards, and direct ourselves towards producing a new industry standard for designing certainly low and medium pressure networks. As I say, Alpha will design and cost this full scale test facility and laboratory campaigns, which we potentially would deliver in a beta phase, because that would take time and probably be reasonably costly. And then there's this complicated modelling to do the cost benefits of what's the balance between changing that gas velocity against increasing the risk of basically breaking something or causing inconvenience or loss of reliability. So one of the things in alpha phase certainly is, in addition, is to do some small laboratory tests to see if the synergism exists between hydrogen damage and erosion damage. In that people have done a small amount of work, but we need to do something a lot more real. I think that's fairly close. Have you got the next slide? Yeah, that's it. That's our part. So yeah, so we've discovered some interesting things. We've discovered one slightly worrying thing about the synergism, but we need to do some fundamental work to show that that is actually a real effect in the gas network environment. And do you get that effect with the type of debris the pipes have got, as opposed to sand, which is what people have used up to now?
I was just going to add in, Tim, if that's okay.
Yeah.
That on the literature review, we were unable to actually find any physical test work that kind of enabled us to establish a safe design velocity limit. So that really led us on to saying, okay, as an industry, we need to do the testing, which is what the alpha phase part is about, to design the testing to then have the beta phase. Because there's not any information out there, sufficient information to provide the test data, the evidence for it. I think that probably rounds us.
Right. We're there, are we? Yeah.
Great. Thank you for that, guys. We're now coming on to the Q&A then for the last few sessions. So I'd welcome any of the presenters back on the screen. If you want to put your video back on, that would be great. Let me take a look at the questions that we got through here. What I'll do is I'll start with the charge project, and if there is anything that you think crosses over with the work you're looking at, please feel free to jump in. So let's dive into the charge project. So in charge, how long did you assume that the transmission system will be transporting methane for in calculating the carbon savings?
I'll take that one. So the needs case for charge, I guess was aware that there was potential for a switch from a methane-based grid to a hybrid methane hydrogen grid, and then in the future hydrogen only potentially, and that was taken into consideration, and all the vendors have been queried on the potential compatibility of their equipment if to those blends that might run through the network in the interim and in a future hydrogen. So that has been taken into consideration. The carbon footprint looked at construction footprint versus operational savings, and it's estimated that it would pay back that construction carbon footprint in much less than a year. Longer term, in terms of tackling emissions in the transition phase, charges the potential to capture, I think the numbers were something like 1,500 tonnes of processed gas per year, which is something like 39,000 tonnes of CO2 equivalent. So we have sort of balanced that potential, considered whether or not this is a short-term solution, and whether the project and the problem is going to be substantially different in the future. But we believe that it still stacks up, and ultimately, if the equipment can be demonstrated to be compatible on blends and future hydrogen-based grid, it's reducing emissions of any processed gas, whether that be methane-based or hydrogen.
Thanks, Gemma. This is maybe a question for the National Grid lead and more widely in the project, but do you consider the potential blending of hydrogen in the gas network in terms of impact of venting gas? And have you linked up with the hydrogen compression project that's in a separate challenge within SIF?
We have, that is like a wholly separate project, I guess, looking at the potential impact of a future hydrogen network, but we have linked up with the consultants working on behalf of National Grid and others on that topic to start to consider impacts of, of whatever that transmission network fuel might be.
Yes, we've definitely done that, Kate, to answer that question. We've been cross-fertilising lessons learned and various design aspects throughout the SIF discovery and linking up with those projects.
Great. I'll just have one more for you guys then. What is the total power that can be gained by using the vented gas, and how is this planned to be used?
So the vented gas would be re-injected to the network. It's not actually National Grid's gas to use, if you like. I know there are some similar capture recompression projects on some of the European networks where they have utilised the gas for other on-site uses, but that's not actually possible for National Grid in the current sort of setup of the license agreement. So it is proposed to capture the emissions and inject them back into the national transmission system. So they're, sort of reducing losses from that transmission system.
Thanks, Gemma. Okay, so we'll go on to the hydrogen barrier coatings project. So an audience member has written, I've read some reports that talk about building a new transmission network for hydrogen so that industrial clusters can be connected whilst domestic gas customers are still supplied with methane. Do you have an estimate of what proportion of the network will need to be repurposed and how much will be redundant?
Yeah, so I'll take that. So I think there's probably talk about Project Union, which is looking to connect the industrial clusters on the east coast of England. So that's the idea of that. They're still defining all the exact routes for that, but it's likely that we will be repurposing sections for 100% hydrogen within Project Union, and then there'll be sort of parallel pipelines that will be supplying methane to customers. So the whole idea is to enable customers to get what they need. So there'll be no disruption for methane customers during the implementation of Project Union. I guess longer term, we're considering blends of hydrogen and methane and deblending technologies as well as a company. So again, we can deliver the required blend of hydrogen or methane to the customers as required. So we kind of have to go, we're making sure our network is capable of 100% hydrogen and blends, and then we can provide whatever mix our customers need, and our suppliers are able to put into the network as well.
Thank you for that. What percentage of or length of the existing network will require coating, and is this spread across the NTS?
So the pie chart that I very quickly showed was a first sort of stab at a high level risk assessment of our current network in terms of the kind of grades we have, and we have some known metallurgical issues mainly related to the age of the current network. So there is a lot of work ongoing to really define that and quantify the risk that we see across our network, but it's likely that probably the older materials, the older sections of pipe, and or the ones that are the most highly stressed, which tend to be the highest strength grades, might be the most at risk for hydrogen embrittlement, and so they may be the ones that might require this at first. But again, it kind of depends what the future scenarios look like in terms of the required gas pressures and velocities that we need to be putting through the pipes, and which could determine a kind of the prioritization and the ability, the need to repurpose in this way.
Thanks, Robert. Just a couple more questions for you guys. So how does longevity of the new pipeline materials compare to metals currently in use?
Yeah, so that was, and I think there's one below, so third-party damage as well. So I'll pass this over to Ton in a second, but just to kind of introduce that. So in terms of the current materials, we use steel, and there's pipeline in the ground that was installed in the 1960s that's still safely operating via use of corrosion mitigation strategies such as cathodic protection and coatings. So they're currently still in use and still working. And I guess Tom, comments about GRE in comparison with steel. You need to go off mute, I think, Tom.
Mute.
Yeah.
Yes, of course, the composite pipelines, they won't suffer from corrosion, so that's not an issue. In terms of, let's say, durability, for example, continuous loading. I mean, in general, these pipes they would perform probably much better than a steel pipe, simply because of the failure mechanism in a composite pipe. A composite pipe is intrinsically very damage tolerant. That means that if there is a crack initiation, that crack will not grow very quickly into a failure. There might be maybe a small cracking going on in the material, but it won't lead to a critical crack that actually would lead to failure of the pipe. So in that sense, these pipes will probably more safer in terms of failure, whereas in a steel pipe, basically you would have an initiation of a crack, and that crack will simply propagate until it reaches a critical state. And in composites, it's much more complicated system where there is basically damage that occurs, but that damage the material in itself is quite tolerant to that damage, so it's not going to lead to critical failure, and as such, I think it will behave better than a steel pipe for sure. Yes.
Thanks, Ton. Okay, I'll just come on to the velocity design questions for Timothy and Jane. If hydrogen flow rates require to be 3 times that of methane, how does this impact on the network running costs?
That's an interesting question, which I'll let Jane answer.
I was going to say, running costs kind of pass on that question, I'm afraid. But as far as that's part of what we want to look at on the cost benefit analysis as to what it's going to cost or the implications of that change in velocities on the mains replacement program that's going on, and then therefore the future running costs of the network. So don't know what the answer is, but that's part of what all of this, along with the other projects on hydrogen, are wanting to look at. So kind of feel like I've opted out of that answer.
So you're just saying watch this space for alpha. I get you. Okay, I'll go on to the next one then. So was there any debris analysis conducted during the high deploy or H21 projects? Might be somebody on the NG side that needs to answer that.
Yeah, I mean, I've been involved a little bit in high deploy, so I can tell you a bit about what was done, because we did basically looked at some of the assets before the second trial. We looked at the iron pipe Win Leighton to look at the condition, and as part of that we looked inside it, see what was there. So yeah, we got a fairly good idea what was inside it at the time, which was actually not a lot of debris, it was a lot of iron oxide, and there's bits and pieces from the Towns gas days, but I don't know what H21 did. We weren't directly involved in that one, so there may be somebody on the call who was.
Maybe a tie-in there that we can offer.
Yeah.
I was going to say, in the literature research, we obviously didn't pick up sufficient the information there that gives us the direct link.
Maybe just to add on that, part of the H21 project is some gas distribution network test rigs being built at Spade Adam. Now, testing for debris is not part of the scope as far as we know at the moment. But if we decide during the alpha phase that it's justified and necessary, that clearly an obvious thing to do would be to look at repurposing whatever test facilities we have to do that. And I see, maybe if I could just skip ahead, Katie, somebody's asked a question about test facilities in other countries, and I think this rounds it up. I think our approach really is to look at what we need to do for it to become an industry standard, for the industry to accept it as valid. So we'll do, if the test facilities or tests have been done elsewhere and the industry accepts them as suitably valid, then we would use them. And that's part of the alpha scope, is to work out, what is it we need to do so that we can create a new industry standard going forward, if that makes sense. If we need to do test facilities, we can do that here just as well as anywhere, I think. But if it's been done or if it's available somewhere else, we would clearly use that.
I mean, part of that is clearly, as D&D, we're pretty much everywhere. So we have laboratories. In fact, one of our flow facilities just happens to be in the Netherlands. But so if we propose a test facility, it will go in the best place. It doesn't have to be in the UK. Equally, we have a large space at Spade Adam where we can build extremely large things safely. So that's a good place to play about with hydrogen.
Thanks, Timothy. And just quickly for the 2 projects, looking at the hydrogen barrier coating and the velocity design, will the debris impact in velocity be impacted by the pipe coating in the previous project? Any takers on that one?
Yeah, Andy's keen to answer that one.
Thanks, Robert. Yeah, that's something that we have to consider for a coating system is does it impact the way that you inspect and use the pipeline, and does the debris in the pipeline cause damage to the coating system that we're using? So, you know, part of that work is to understand how to protect the barrier coating, which there is a gas barrier, from life in the pipeline, and then think about, well, how often do you need to go and, you know, protect that coating and inspect it to make sure it's still effective. So those issues are very important, and that's, you know, something we'll consider going forwards.
Thank you, Andrew. We're running out. Yeah, if it's a quick point, Jane, we'll take it.
The other project, the coating one, was looking at the NTS, and clearly a lot of the costs associated with the mains replacement and the velocity for the networks is on their lower pressure tiers. So it's the velocities around those that are equally as fundamental, and that's where we don't get the coating. It's actually what debris in, whether it's new PE pipes or old PE or the old pipe, is just the physical network. So there is a link, but perhaps not as much as you might think.
Thanks, Jane. Thanks for that. Thank you for all the speakers that have come this afternoon. I'm just going to share just a few bits of information just in case. We have a number of other show and tell webinars taking place. So we've got our Data and Digital Challenge taking place tomorrow and Monday. You can see the different themes on the screen, and I think Chris has just shared the link in the chat. And then on Monday we have our whole system projects. Look at that, wrong way round, but they're happening all on Monday. So if anybody on the call is interested, it's worth checking that out. And then the last thing that I just wanted to say that I mentioned very, very briefly at the start of the call is we've actually published our round 2 challenges. So a lot of the heat projects that we've had today have been focused mostly on the transmission network, or the impacts on the transmission network from an electricity point of view, and the gas network. This time round, the challenges are open to both the distribution networks on gas and electric, and the transmission networks on gas and electric. So we've announced our next round of challenges that you're seeing on the screen. There's a launch event taking place next Wednesday, 1 in the morning, 1 in the afternoon. And there's an opportunity for anybody on the call who wants to find out how to get involved in SIF and in future rounds, and if they've got any ideas that they want to put in front of the networks, this is an opportunity to find out how you can do that. So best way to keep up to date on the SIF is to sign up through our newsletter, but also this is a great opportunity to find out what's next. So just as a closing thought, thank you so much for everybody taking the afternoon to attend today, particularly the projects. Congratulations to getting to this stage, and thanks again for presenting. Thanks again.
Thank you.
Thank you, Katie.
Thank you.
Everyone.
Thank you, Kate.
Thanks, Kate.
Thanks, Kate.
Thanks.